please. Welcome everybody to this second session of the probability seminar, joined University of Chile and Universidad Católica, this time Universidad Católica, and we have the pleasure to have our home speaker from Universidad Católica, Santiago Saglietti here, and he will talk about his new result on the cover time in planar domain. So please, Santiago.
Thank you, Ida. Presentation. I'm on. Okay, so this is just. This is a joint work with Oren Louidor from Technion, who you might know. He comes to Chile once in a while. And it's a relatively new result. It's an archive, been an archive for a couple of weeks. So, oops. Okay, it's not working. Disable scrolling.
Santiago algún F5, F11, F12.
Control L, este
¿Y la flechita de arriba a la derecha? Vamos a poner un video.
que en la grabación se vea Santi.
Sí.
Está escribiendo.
Pero sí, como cámara. Esto no funciona, pero el siguiente sí. Okay, so welcome everybody. Okay, so I hope this works now. So let me tell you about the model that we're going to be studying. So we're going to start with a nice bounded domain. By nice, I mean that it's a nice boundary. Don't have to worry too much about that. And it's an open connected set of R2. Okay? It's a continuum domain. And for each n, we're going to consider the n-scale discretization for domain D, which is essentially given by scaling the domain by n and then intersecting it with C2. Okay? So I hope you can see more or less. Maybe the domain for the purpose of this talk is as a ball. You scale this by n, and then you discretize this so you get a squared ball. Okay? And I'm going to call this discretization of my domain Dn. Okay? And now I'm going to add a boundary to Dn. Which is obtaining the following. So imagine, so what I'm going to do is I'm going to take all the sites which are on the boundary of my discretized domain. Here you can see them there, okay? And I'm going to join them all to a unique vertex which I'm going to call the boundary vertex, or otherwise partial, okay? And then I'm going to consider the graph of C2, which is this discretized version of my domain D with the boundary vertex. Okay? So basically, this is what I'm going to consider. And I'm going to call this graph Dn hat. Okay? So it's the discretization plus the boundary which is contracted into a single vertex. Okay. Okay, and so inside, so this is a graph here. Okay. So in this graph, I'm going to consider a continuous time simple random walk, xn, okay, on this graph, which is going to start from the boundary vertex, okay, and it's going to have edge transitions equal to 1, edge transition rates equal to 1. So what does that mean? That the random walk, okay, say it starts here, but then if at some point it touches this point, then from this point it's going to weight an exponential, like a random time, which is an exponential random variable with parameter equal to the number of neighbors, okay? And once that exponential clock rings, it's going to choose one of the 4 neighbors at random and jump to it, okay? And then it's going to wait for another exponential time, which is independent of the previous one, and jump again and jump again. And so when the random walk is inside the bulk of the domain or the interior of the graph, the time it takes to jump is this exponential random variable of parameter 4. But if it's in the boundary, it's going to jump much quicker because it has many more neighbors. It's going to stay a little time in the boundary. Okay, and so the quantity of interest is this quantity here, which I'm going to call Tn cover of hat, or Tn hat cover, which is the cover time of this graph Tn hat. Which is essentially, the time it takes my continuous time simple random walk to visit all the vertices on the graph. And the question that we're interested in is, okay, what happens with this random quantity as n goes to infinity? Can we say something about the asymptotics? So is the problem here? Okay, so the main result that we have with Oren is the following. So if you take this cover time, okay, so if you take this cover time and divide it by the number of vertices in the graph times log n, and you recenter this by this other quantity, okay, then as n goes to infinity, this recentered cover time is going to converge to a specific limit, okay, which is a sum of 4 terms essentially. G is a random variable which has Gumbel distribution. So that means that it has this distribution function. Then we have log of, the modulus of CD, where CD is the critical Liouville Quantum Gravity Measure with respect to the continuous Gaussian Free Field on the domain D. If you don't know what this is, doesn't matter, I will tell you in a little bit. You don't need to worry about this. But the important thing for now is that the modulus of CD is just the total mass, okay? So this CD is a random measure on the domain D, okay? And what I'm taking is the full mass of the measure, which is a random variable, okay? And then I'm taking the log, and this is what you can see here. Then this third term is just a centered Gaussian random variable, so mean zero Gaussian random variable with some variance, sigma d squared, which is explicit, but I don't have space in the slide to put, so I will put what the variance is in a little bit, well, maybe in the end. And C star is just some constant, okay? And, so the other thing that I need to say in order to kind of characterize the limit is that this Gumbel random variable is independent of the other 2 random quantities which appear in the limit. But these 2 quantities are correlated to each other, okay? And I need to tell you exactly what's the correlation between these 2 quantities, but I will tell you about this later. Okay, so this is kind of the first result, which basically characterizes the asymptotic behavior of the cover time. Okay? And the second result is that if you consider the last visited vertex by the random walk, so that means the position in which was visited last in the graph, okay, before the cover time, Then what happens is that if you scale this position by n, then this also converges in distribution to a specific limit. And this limit has the following distribution. So the probability that the limit is A is essentially the expectation of this right here, which is, if you recall, the Liouville Quantum Gravity Measure divided by the full mass. So this is a probability measure now, okay? And you take expectation. And okay, so yeah. And as a matter of fact, we kind of have a joint limit. So the quantity from the previous theorem and the last visited vertex converge a distribution jointly, okay, to a vector which has the following law, which is I can explain what this is. So the law of the limit is characterized as follows. So if you condition on the Liouville Quantum Gravity Measure and on this Gaussian random variable h bar, then the law of this vector is just each coordinate is independent. The first coordinate corresponding to the cover time is just okay. There's a constant here, it should be here. Don't worry, you can erase this. It's this sum of these four quantities, okay? And the law of the last visited vertex condition on these two things is just a normalized critical Liouville quantum gravity. Okay. Yeah, so I meant to say that so in the previous theorem, by the way, is this clear? So in the previous theorem, there are a bunch of multiplying constants like 1 over 2 pi, which I kind of omitted on purpose because it's not the only multiplying constant that should be there. There should be another one here. But in order to keep things simple, I kind of erased all the constants because in a little while they start to become annoying. So modulus of multiplying constants, this is the actual limit that you get. Okay. So so some remarks before I comment a little bit more about the problem. The starting vertex of the random walk is not important. You can start in any other vertex of the graph and you will get the same asymptotics. That's because the time it takes you to go from the boundary to any given vertex and back is much smaller than the order of the cover time, so it doesn't really matter. And if instead of considering a continuous time random walk, you consider the discrete time simple random walk, which jumps at integer steps, then the same asymptotics hold, but you need to divide the cover time by 4. So instead of, let me go back 1 second. So instead of putting the cover time for the discrete random walk, you need to put the cover time divided by 4, and then the rest is the same. Okay? And that's because, okay, so if you see what happens in this continuous time and random walk, the time you need to wait before you jump is an exponential random variable of parameter 4, essentially. So that essentially tells you that it takes you 1/4 unit of time to make a jump. And the discrete time simple random walk takes you 1 unit of time. So you need to multiply by 4.
Something?
Yes.
But when you're in the boundary,
Yes.
it's very
But
different discrete.
Yes, but that doesn't really matter. Yeah, because you spend much more time than in the boundary. Okay, and one last thing is that, okay, maybe these boundary conditions are a bit weird. Maybe you would have thought of another boundary condition, for example, not having a boundary, or maybe making the graph periodic, so to have a torus, n by n torus. And okay, we do this for convenience reasons, but a similar form of limit is expected also for these boundary conditions. Okay, but it's open. But the same kind of limit should hold. Okay, so a little bit of history of the problem. I don't want to go much into this. Just to tell you that people have been thinking about this problem since '89, and they have been studying different variants of this problem. periodic boundary conditions or wide boundary conditions for random walks or ground motions or changing the graphs a little bit. And well, we've had like partial progress, and this result will be like kind of the first result for something which is similar to the original problem, which is a random walk on a lattice, two-dimensional lattice, and okay, this time with wide boundary conditions. So the original problem was not worse. So don't worry about this. But it's been a problem. Okay, so the people have been working on this for a while now, and people conjecture that this limit should hold. So it's been conjectured or known for a while that the cover time should converge to something which is a Gumbel random variable plus a sum of independent things which are related to the critical Liouville quantum gravity. And why is that people knew beforehand that this limit was going to hold? Well, it's because this problem essentially is about studying the extreme values of a log correlated field. And I will explain what this is right now. And but it turns out that all log correlated fields have extremes, maxima and minima that have supposedly universal behavior. And so, okay, so let me explain this slide. So, let us define the local time at a given site of our graph by this. So this is essentially ln of t of x is just the amount of time my random walk spent at x from time 0 to t. Okay? And if you define these variables, okay, then the cover time can be restated as the first time in which all these local times are positive. Okay? Or in other words, in which the minimum of this field of local times becomes positive. Okay? And so it turns out that the cover time is what we call an extreme order statistic of this field. Okay, of the field of local times. And it turns out that if you consider a simple random walk on a planar domain, so 2 dimensions, and also in trees, but for this talk we're going to focus on 2 dimensions, then the local time field of a simple random walk has logarithmic correlations. Okay, so that means that if you consider the covariance of 2 points in the graph, then this behaves essentially like this. Okay? So the way we need to understand this is that if x and y are very far away, so maybe okay. Yeah, so if x and y are very far away, they're going to be at distance roughly n apart in the graph. And so this quotient will be 1. And essentially the covariance will be, okay, let's say order 1. Okay? So that means that they will be very little correlated. Okay? But if x and y are close, let's say at distance 1, for example, then you have logarithm of 1 over n, and this is going to explode. So the local time field of points which are very close to each other have very big correlation, and of points which are very far apart have very little correlation. And and it turns out that the extreme value statistics of fields with these kind of correlations are supposed to be universal. And in particular, they should satisfy a limit like the one I showed you before. This is not working very well, but essentially the maxima or the minima of the log correlated field should behave like something which is log minus log of something, and you should get converges to a Gumbel plus something independent, and all the things that I told you before. Okay? This has been verified in a very few particular cases, but it's conjectured to hold in general. Okay? And once people realize that the local time field of a simple random walk had this behavior, then they said, okay, maybe this is going to converge to a Gumbel plus something. Okay? And the scaling should be more or less the one I told you. Okay, so this is why this was conjectured before, and but okay, coming up with the proof was a bit difficult. Okay. So, in general, for a low correlated field, I don't have any heuristic why the maximum should converge to a Gumbel random variable plus something independent. But for the particular case that we're dealing with today, the cover time, I do have a heuristic that I want to share with you, okay, which is kind of the main idea behind the proof of our theorem. So I guess it's important that I tell you this. Okay, so I'm going to shift to an easier problem, which is the coupon collector problem. Okay? So I'm going to consider a variant of this problem, which is in continuous time. Okay? So suppose, I guess you all know the coupon collector problem, more or less. Okay, if not, you're introduced to it now. So suppose that a collector buys coupons at rate 1. So that means it waits for exponential random time of parameter 1, and then it buys a coupon. And there are k different coupons to collect, and each time he buys a coupon, the collector, the collector buys a coupon, it chooses a coupon at random among the k possibilities and buys the coupon. Okay? Independently of all previously bought coupons. So, okay, this is the problem, and the problem in general is to determine how long it takes to complete the collection, okay, to buy all the coupons. So it's kind of a well-known thing that if you define tk as the time it takes the collector to buy all coupons, then if you divide tk by k and subtract log of k, this converges the distribution to a Gumbel random variable. Okay? And the reason why this happens is that is the following: is that if you, for each coupon, let's say from 1 to k, you define this random variable, hi of k, which is the time it takes the collector to collect the ith coupon, so to buy the ith coupon for the first time. Okay? So by properties of the Poisson process, it turns out that these random variables are IID, exponentials of rate 1 over k. Okay? And furthermore, the tk, the time it takes to complete the collection, is just the maximum. So, so basically, what you need to understand is the asymptotics of the maximum of IID exponential random variables. And this is something which is very well known. Okay? So from there you can kind of conclude this theorem that I was telling you about. But what happens now if you consider a kind of a generalization of the previous problem, in which for each natural number n, you consider a problem in which now you have a random amount of coupons, which I'm going to call kn. Okay? And conditionally on the amount of coupons, each coupon is purchased independently, not at rate 1 over k like before, but at rate Rn. Okay? This is going to be another rate which is going to go to 0. Okay? And okay, Rn is going to be deterministic and it's going to go to 0 as the number of coupons increases to infinity. And furthermore, let us assume that there's a scaling limit for the number of coupons in the problem. Okay, so if you divide by some quantity going to infinity, this converges in distribution to some random variable c. Okay, this is what we're going to assume. So if you assume that, it turns out that the time it takes to complete the collection, okay, divided by this minus log, converges to a Gumbel plus the log of c. Okay, which is the same kind of limit that I was getting in before. Okay. Where g and c in this case are taken to be independent. So this suggests that, okay, if you consider a coupon collector problem in which you start with a random amount of coupons and the amount of coupons somehow satisfies this asymptotics, then you can get this type of limits. Okay? So the idea of the proof of our theorem is going to be essentially the following. So this is kind of the main feature to take home. We're going to run the random walk for a long enough time, okay, until there are only a few sites left to visit. Until you visit most of the graph except for a few sites. I'm going to be more specific later, but for now, let's leave it at that. Then, once we do this, we're going to show that the way in which the random walk visits the remaining sites until it covers everything behaves like a coupon collector problem. Okay? So you can think of this, of the original cover time problem as a coupon collector problem, but there's a, so you can think like, okay, like a site here would be a coupon, and if you visit the site, then you collect the coupon. Okay? But there's a big difference between the coupon collector problem and this problem. The difference is that, okay, if you collect this coupon, the next coupon that you're going to collect is not going to be chosen independently among all possible coupons, but it's going to be one of the neighbors. So there's much more dependence here than in the coupon collector problem. But what I claim is that once you visit most of the graph, the rest of the problem becomes a coupon collector problem. And so what you need to do is to determine the amount of coupons that you have and the rate of purchase. So how long it's going to take you to collect each of these coupons in this new problem, and show that a scaling limit for the number of coupons, okay, and identify the limit. Once you do that, you combine this with what I told you in the last slide, and you get the result. Okay? So that's more or less the heuristics of your so we need to determine how long to run the walk until this becomes a coupon collector problem, to understand how many coupons we have, what's the rate of purchase, and what's the scaling limit for the number of coupons. That's all I know. Okay. So how are we going to do this? The way that we're going to show all of this is by comparing our local time field with another low correlated field, which is better understood. And this other low correlated field is the discrete Gaussian Free Field, which I'm going to define in a bit. Okay? So, so in order to compare the local time field with the discrete Gaussian Free Field, I need to reparameterize time. Okay? So I'm going to define so this random variable, okay, Rn of t, which is the total time that you need to walk, that you need to run the random walk for, okay, until it spends t time at the boundary vertex, okay. So basically, if you measure the amount of time that you spend at this partial symbol here, well, Rn of t is the thing that you need to put here in order to get the t. Okay? Okay, and we are going to say that Rn of t is the total running time that has passed until partial time t. So by partial time, I mean the time spent at the partial vertex. Okay? Okay, and so with this, I can define a new version of the local time field, which is measured not according to standard time, but according to this partial time, the time spent at the boundary. So I define these new random variables, ln of t at x, which is the local time spent at x until partial time t. So until I spend t amounts of time at the boundary vertex. And I can also define a version of the cover time in this new time parameterization, which is just the total amount of partial time that I need to spend until I visit all of the graph. Okay, and so once I reparameterize time according to time spent at the boundary, in order to prove the main theorem, I need to prove these two things. Okay? So don't don't be scared by the square roots. The square roots are there only to simplify the formulas a little bit. There's an analogous limit without the square roots. I don't want to get into that. It's just think of this as a scaling limit for the cover time measured with respect to time spent at the boundary. Okay? So as n goes to infinity, if you take this cover time reparameterized according to time spent at the boundary, then, okay, if you recenter this by this quantity, which has the same structure as before, log minus log log, then you converge to this. Okay. Where, okay, as before, this is the critical Liouville quantum gravity, this is a Gumbel random variable, this is a constant, and these two things are independent. Okay? And okay, so basically this tells you more or less what we want to know for the cover time if you measure time according to time spent at the boundary. Okay? So in order to obtain the original result, we need to kind of deparameterize time, go back to the original time parameterization. Okay? And so this is the other result that we're going to need, which tells you that so if you wait until you spend this amount of time in the boundary, and this time is of the order of the magnitude of the cover time, okay? Then it's driving me crazy. Then the total running time of the walk divided by divided by the total number of vertices, the square root of this behaves like the square root of the partial time of the boundary, plus a Gaussian random variable, which has mean 0 and has an explicit variance that I will show you in the end. Okay? And this is the random variable which was appearing in the original game. Okay? So, so basically, if instead of this time here, which is kind of the expected order of magnitude of the cover time, measured with respect to time spent at the boundary, we could put the actual cover time, okay? Instead of putting this, we put this here. Then this becomes the real cover time. And what this tells you is that the difference between the real cover time divided by the number of vertices and the cover time measured in terms of the time spent at the root is approximately Gaussian. Okay? And so now if you sum both equations, basically you get equation. Okay? Yes.
So you said that the critical Liouville quantum gravity and HD
Yes.
are not independent.
Are not independent. So you cannot sum everything because they're not independent. Okay? But so you can sum things if you show joint convergence. So this is what we need to do. We need to show joint convergence of the cover time measured in this partial time parameterization with the time conversion.
So theorem A and B separately wouldn't be theorem. You need a joint theorem.
Yes,
A and B.
exactly. Okay? But this is too complicated. Okay. So start I will continue until I talk. Okay, so let me define what the Gaussian free field is and the Liouville quantum gravity. Okay? So the discrete Gaussian free field on this graph, dm hat, is a centered Gaussian field. So it's a collection of Gaussian random variables indexed by the sides of the graph, which are mean 0 and they have this covariance. Okay? 1/2 times the Green's function for the random walk, which is given by this. So the Green's function at x, y is just the expected amount of time the random walk spends at y, starting from x, before it hits the boundary. Okay? Yes, so tau partial is just the hitting time of the boundary. And okay, this Gaussian free field is a canonical example of a low correlated field, and the extreme values of the discrete Gaussian free field are very well understood. In particular, it's known that the maximum of the Gaussian free field has this order of magnitude, okay? Which is a quantity that I'm going to call n, okay? You don't need to remember what this is. You only need to remember the following thing, that the order of magnitude of the Gaussian free field, which I'm going to call mn, is much smaller than this quantity, which is the expected order of magnitude of the cover time. Okay? Because here you have 1/4 and here you have 3/8. Okay? Okay, so this is bigger by your subtract. So this is okay, and it turns out this is a theorem that Marek, this book, and Oren showed a few years ago. That which relates the maximum of the Gaussian free field with the critical Liouville quantum gravity. So what the theorem says is that there exists a random measure on the domain D, okay, which is it's a finite measure, but it's not a probability measure, and it's random. Such that if you take the minimum of the Gaussian free field, you can also take the maximum, but let's take the minimum, and you subtract minus mn. Okay. Well, this is going to converge in distribution to a Gumbel random variable plus, the logarithm of the total mass of this random measure. Okay. Okay, where G is a Gumbel random variable independent of this random measure, and in addition, if you take the place, the location in the graph where this minimum was achieved, and you divide by n, then this converges in distribution to something which is the expected normalized measure. Okay? And it turns out that this measure has a name, and it's called the critical Liouville quantum gravity. Okay? There are several ways to define this measure ZD. You can also take this measure through some other means. But for the purposes of this talk, the measure, the critical Liouville quantum gravity, is going to be the random measure which satisfies this. Okay? There's only one measure that satisfies this. Okay? And this measure basically tells you what's the order of the minimum, okay, and the position of the minimum for a Gaussian free field. Okay? So it kind of stores the information about the extreme values of the Gaussian free field and where they are located. Okay? That's what you need to keep in mind. And so you see that if you take the definition of a Liouville quantum gravity as the measure which satisfies this, okay, then essentially the theorem that we show with Oren tells you that there has to be some relation between the local time field and the Gaussian free field, because the same object disappears in both cases. And this relationship is given by something called the isomorphism theorem, which I'm going to explain next, which gives you a sort of implicit relationship between the Gaussian free field and the local time field of the random walk. Okay? So what the theorem says is the following: if you fix some n at a given time, there exists two Gaussian free fields, Hn and Hn prime, on the graph Dn hat, such that the local time field of the random walk is independent of the first of these Gaussian free fields. Okay? And for all sides, we have this equality. So the local time spent at x, this is measured with respect to time at the spent at the boundary, okay? Plus the square of the first Gaussian free field of the independent Gaussian free field is equal to the square of the second Gaussian free field plus square root of t.
This is even starting SNT?
Yes.
Yeah, there is a zero boundary.
Yes, the zero boundary, yeah. Because, okay, I define the GFFs like implicitly like having zero boundary because this is, yeah, you're right. Okay. And so what happens is that the isomorphism gives you an indirect relationship between two collection of points. The points which have not been visited too much, which have a local time which is close to zero, and the points for which the Gaussian free field on the right-hand side is close to minus square root of t. So why is that? So suppose that you have an x for which hn of prime is close to minus square root of t. So if you put minus square root of t here, well, this cancels with this one, and you get that the right-hand side is close to zero, right? So if the right-hand side is close to zero, that means that the left-hand side must be close to zero as well. But the left-hand side is a sum of two non-negative quantities. So if the sum is close to zero, that means that the two quantities must be close to zero. The local time, but also the square. Okay? So this tells you that the set of x's, for which the right-hand side is close to zero, or this hn of prime is close to minus square root of t, is the intersection of two sets. The sets which have a low local time, and the sets for which, and the x's for which the Gaussian free field on the left is also close to zero. Okay? And mind you, these two sets are independent because the L is independent of the H. Okay? Okay. And so, okay, so let me, yeah, let me explain this and then I'll have to skip a few slides. So if you basically look at this, which is kind of the set that one would be interested in if you're looking at the cover time, so you want to see when this set becomes empty, okay? What I'm claiming is that if you take this set and you intersect it with this, then you get this set, okay? So the set on the left-hand side is a thinning of this of the set of this first set, okay? So in other words, if you want to construct this set from this other set, okay, what you need to do is take each x for which the local time is close to zero and look at its value of a Gaussian free field on the left, okay, which would be, it would be the same as flipping the coin. So if the coin is heads, which means that the hn of x is close to zero, then you keep it and it appears on the left-hand side. If the coin is tails, which means that this is not close to zero, okay, then you will throw it away. Okay? So the point is that, okay, you want to understand this set, which you don't understand, but this set we can understand very well because it's related with the Gaussian free field, which is a much better understood object. Okay? So the problem is, if you know how thin set looks like, can you recover the original set or not? Okay? And if the coins that you're throwing are independent, okay, for each x, then you can do this because it's an independent thinning and there's no problem. Okay? From the thin set, you can reconstruct the original. But the problem is that the points that you're tossing for each of the x's, which would be the values of hn, are not independent because the Gaussian free field has correlations. So this makes it more complicated. This is kind of the main problem behind what we're trying to do. Reconstruct this set from this guy, knowing that it's not an independent thing. Okay? Nevertheless, okay, the thinning is done by a Gaussian free field, so since we understand the Gaussian free field very well, we can still do it. It's not complicated. Okay. Yeah, so if you give me like 10 minutes, I think we can. So the idea of the proof of the theorem, or at least one part, the first part about the cover time measured in terms of time spent at the boundary, goes as follows. So what we're going to do is we're going to split this time window since the beginning until the cover time into two phases. Okay? One phase until the random walk accumulates this amount of time at the boundary. Okay? Where this TA of n is just the square of mn, which is the order of magnitude of the Gaussian Free Field, which I told you before is much less than the cover. Okay? So this is the time I told you before that we're going to run the walk for a long time until there are few sites left to visit. This is the long enough time. Okay? This square of n. And then we have a second phase in which from this time onwards we study how to complete the graph, how to cover the entire graph. Okay? And so since TA of n is much less than the cover time, by the end of phase A, there will be many unvisited vertices. And so what we want to do is understand the geometry of the set of unvisited vertices after this long time corresponding to phase A. And then, once we understand the geometry of this set, we need to calculate how long it will take to cover this set. Okay? And here the geometry will play kind of an important role. And so, okay. So what we want to do for phase A, we want to understand the geometry of the sets of sites which have not been visited after this time. Okay? So by the isomorphism, I told you that there's a correspondence between this set, okay, and this is very annoying, between this set, okay, the set of x's for which the right-hand side of the isomorphism is close to 0, and these two, okay? And well, it turns out that the set on the left, okay, is just the set of x's which are close to the order of the minimum of the Gaussian field. Okay? And the set of x's which are close to the minimum value of the Gaussian field is very well understood. So this set is very well understood, and from this we want to understand this. And okay, it turns out that using this relation, we can show that the set of unvisited sites is arranged into clusters of unvisited vertex. So you have the entire domain here, and you're going to have like small clusters of points which are not visited. Okay? Each cluster is going to have typically diameter which is order 1. It's not going to grow with n. It's going to be finite. Okay? And all these clusters are going to be very far apart from each other, at least this distance apart. Okay? Moreover, what we can show is the total number of clusters when divided by square root of log n converges. Okay, this is again wrong. Sorry, it should be a constant times the total mass of the Liouville quantum gravity. Okay? And moreover, the location of these clusters, if you look where the clusters are, you consider, for example, the empirical distribution, then asymptotically this empirical distribution behaves like the normalized critical Liouville quantum gravity. Okay? So this is all that we can show using the isomorphism. And, okay. So, since clusters are order 1 in size, okay, and they're very far apart from each other, essentially you can think of clusters as single points because they're so small compared to the entire graph, and that you can think of them as points. Okay, so once you visit a cluster, it's very likely that you will cover the entire cluster before doing anything else. Okay, so you can think of them as points. And also the probability that you visit one cluster and then you visit another one before going back to the boundary is negligible. So you can think that you collect clusters like one at a time, okay, between excursions from the boundary. Okay. So this allows you to treat the second phase in which you finish completing or covering the graph as a coupon collector problem, in which each coupon now represents not a site but a cluster. The number of coupons is approximately this, and each coupon is collected at this rate, which is the exit rate from the boundary times the probability starting from the boundary that you visit a given cluster, which is essentially a given point in the bulk of the domain. So this is very easy to estimate using Green's function asymptotics, and so now you can plug in the asymptotics I told you before for the coupon collector problem, and this gives you that. Okay? So this is how long it will take you to complete covering the graph after this long time of phase A. So once you sum the amount of time you spent at phase A and you do a bunch of computations, you get this, which is how I'm doing here. Okay. So you have 2 minutes. I'm going to try to explain what's the relationship between 12 minutes between this Z and this H. Okay. I'm just going to throw things at you. I'm not going to explain too much why they're true, but just so that you have an idea. So we need to work in order to explain what's the relationship between this Liouville quantum gravity and this H bar. The limit, the time conversion. We need to work with a version of the Gaussian Free Field, which is called the zero average Gaussian Free Field, which is essentially a Gaussian Free Field conditioned to have a zero average. Okay? And that gives you a new field. Okay? So this HN bar is just the average of the Gaussian Free Field, which is a Gaussian random variable, and I'm conditioning this Gaussian random variable to be 0, and this changes the law of the original Gaussian Free Field, giving you this zero average version. And okay, turns out that if you have a regular Gaussian Free Field, you can decompose it as the sum of 2 independent quantities. One, Hn hat, is a zero average Gaussian Free Field, and the other one is the average of the field, okay, times a function field, okay, so which is deterministic. So this psi n is a deterministic field defined on the vertices of the graph, which multiplied by the average gives you this decomposition. Okay. And the point is that the zero average Gaussian Free Field and the average are independent. Okay, so there's no last slide. Yes. Yeah, this is the last slide, I promise. Okay, so the theorem that kind of relates this HD and the Liouville quantum gravity is the following. So if we take the continuum Green's function on the domain D, not the one I showed you before, but actually the continuum limit of this, then this function psi n from the previous slide converges pointwise to this explicit function, okay, which is an integral of the continuum Green's function. And the average of the Gaussian Free Field will converge to a Gaussian random variable with this variance, and this variance which is given by this formula. And this is the HD from the first theorem. Okay? And moreover, what happens is that there exists an explicit random measure CD hat, which is independent of the average of the Gaussian Free Field. Sorry, it should be of HD. Okay, not HN, but HD here. Of the limit. So that the following representation holds. So this is the Liouville quantum gravity, and this is correlated with this via this formula. Okay? When you take this measure and this this measure here, C hat, is not just any measure. It's actually the zero average version of the critical Liouville quantum gravity. So it's the measure that satisfies this theorem, okay? But for the zero average Gaussian Free Field instead of the original Gaussian Free Field, which is something that wasn't known, that we had to prove and then show that there's this relationship between the two critical Liouville quantum gravity measures. This is kind of part of the theorem. But okay, so that's all I wanted to tell you.
Just a quick question. What is new in this paper compared to the old paper?
And
What's this new paper? What's added compared to the old paper?
which old paper? So the old paper.
Where you had the diagonals result. What was added now?
Okay, so
This last one.
so in the previous paper we showed that this quantity was tight, okay, and now we show that it actually converges. So essentially, okay, there are a bunch of things which are added, but the main ingredient which was missing before is that for this paper we showed that once after phase A you have all these clusters of unvisited sites. If you look at the local time field on each of these clusters, what you see is something which is IID. So the local time field inside each cluster of non-visited vertices is IID. And this is something that we couldn't show before. But now we kind of found a way to show this. And using that, so before we knew that the number of coupons after phase A was of the order of square root of log n. This is what we knew from the previous paper, but yeah, it's not here. But using that these clusters are have an IID structure, now we can actually find a scaling limit. So this is kind of the main part, which is new. Okay, and something which is also new is that now we need to show joint convergence of all these quantities because we want to kind of sum everything and there's so many correlations. That's kind of the main need.
Just to see if I understood, this is when this small cluster they appear, somehow you are each time you go and you just catch one cluster.
Yes.
And then you go back to the boundary.
Yes.
And then you catch one cluster.
Yes. Because they are so far apart that the probability of visiting two in a given excursion is negligible to just visiting one. And so basically this tells you that each time you visit one, if you visit only one, it's almost the same as buying a coupon.
And how do you, so there is, well, I think you discussed about it a lot, but I'm still not getting in my head. How do you, in a way you have to say that the amount of one you are seeing, is you can get it, the total amount you can get it from just the one you are seeing when you blur out by a GFF. Yeah, so like you are seeing the zeros, but you are not seeing all the zeros.
Yes, exactly.
So how do you manage to, which is essentially controlling that the blurring is not being that bad?
So you kind of need to reverse engineer everything. So it's delicate, and okay, you need to do this like different parts, and in different parts you need to do it differently. But the heuristics is that if the local time field would be behaving like in a funky way somehow, this would show up in the Gaussian Free Field. Because even though the Gaussian Free Field is a dependent thinning structure, you still understand it very well.
Yes.
So this kind of prevents the local time field from behaving like in a too strange fashion, because you start seeing this on the right hand side.
And is it has to do with so there are either two things. It doesn't have to do with mostly the series of the GFF or mostly the GFF condition to be positive. So which object did you have to look at? Like at the series of the GFF?
Both. So this is the object that you understand very well, and but this you not very. You don't need like a lot of information about the series of the Gaussian Free Field, but the probability of the Gaussian Free Field being close to zero is something that you can compute. Yes, it's just the Gaussian.
It's like 1 over square.
Yeah,
just
exactly.
the 1 over square root log n.
Yes, and essentially that gives you minus.
Okay, so like you don't need to say somehow like independence between these zeros and the
No.
okay.
No, and the thing is, okay, so one more thing. You kind of have so the fact that the clusters, so the Gaussian Free Field also have clusters of points which are close to the maximum. And you know that these clusters are very far apart. You already know this because people have studied the Gaussian Free Field and they know this. So this tells you that this gives you some space somehow in order to on the left hand side. So because you only need to give me a second. So the clusters. So okay, so let's say this set is arranged into clusters. Okay, so that means that if you're gonna check things in different clusters, then these things will be mostly independent. Okay, because the clusters are very far apart. So this is the way you kind of construct an independent thinning from a dependent one. You use
so you really need to define the definition of clusters because like polynomial length or something like that. So n is like square root of n or something.
Yeah. Well, okay, not because the clusters here are finite. The clusters in the Gaussian Free Field.
Yes.
So you can only it suffices to take like finite clusters, and you can see that the clusters, all the other clusters which are perhaps not of a finite diameter, you can discard because there are not many of them. So you can visit them very quickly.
I see you can show that like after a finite diameter you can separate. It's really like if you show me, I will be able to see this is a cluster, this is a cluster.
Yes.
Like there is a like algorithmic deterministic way to define a cluster of both type of
let's say yes. So we kind of so the way we define clusters is we kind of take a grid and you see if there's something unvisited inside or not. And so if there's something unvisited inside, okay, this is already kind of a cluster. But then you realize that the diameter of the cluster is actually much smaller.
Okay, so there are usually no two two squares, one close to the other.
No, usually no, because so if you see this, then if you see this a lot, then you would see this on the right hand side for clusters of the Gaussian Free Field close to the maximum or minimum. But this has like a Liouville measure like very close to zero, so you will not find the maximum. Yeah, sorry, this is all very in the air. But okay, more or less, if you understood the problem.
So we know something about the local time field, so what it converges, and if we like stop it at the cover time, what it would look like? Like something like a GFF with a mark point?
Probably we can say something about this. I don't. No. So there. Probably we can say something. Okay. Let me say first thing. So the fluctuations of the Gaussian. So if you kind of recenter at the right, you converge to the Gaussian. But also, if you look at times which are close to the cover time, you should be able to get like a scaling limit for the local time field. I don't think this has been done. Maybe you can come from this analysis. And what people have done is look at the local time field at times which are multiples of the cover time, which is kind of easier. And then they have a scaling for this. Now I did this. So what we're trying to do next is not for the local time, but for something which is related, which is the field of heating times. We're trying to find a limit for the field of heating times.
First time you hit every vertex. What do you mean by it?
Yeah, so the h of x is the first time you hit the vertex, and then you, the field of heating times. Exactly. So the maximum heating time would be the cover time, but then you understand the structure of heating times. This should also be kind of a follow-up